This is the fifth and last video in a series of videos I prepared for my honors chemistry class about chemical bonds. And this one focuses on intermolecular bonds, also called intermolecular forces of attraction. So when electrons are shared in a covalent bond, the sharing is not always or even usually equal. So we have to get a couple terms out of the way before we can really talk about intermolecular bonds. So what is the property that determines how electrons are shared? And this comes down to the electronegativity of the elements involved. If we have two atoms like fluorine and fluorine, then they are the same strength, so they're both going to be tugging equally on those bonds, and we'll get a perfect even sharing of electrons. However, if we have two atoms of different electronegativity values, then my more electronegative element will pull harder on the electrons from the less electronegative element. So as a quick reminder, what's my trend in electronegativity? And for electronegativity, I am going up and to the right on the periodic table, specifically fluorine being my element with the highest electronegativity. That we don't usually think about the noble gases having electronegativity values because they mostly do not participate in chemical bonds. And remember, all we're dealing with are nonmetals here, because intermolecular bonds is we're dealing with molecules formed from nonmetals, for the most part formed from nonmetals. We saw a couple of examples when we were doing ionic bonds where we can actually get molecules from a metal and a nonmetal. As an example, aluminum iodide is a metal cation from aluminum, a nonmetal anion from iodide, but it still ends up being ionic. You can look back to the video on ionic bonds to understand exactly why that is the case. Alright, so why does the more electronegative element not just flat out steal those electrons from the less electronegative element? And that's once again because we're dealing with nonmetals here. So it does not steal because the nonmetal's not a pushover. Somebody like carbon is not just going to give up its electrons willy-nilly. It's not somebody like sodium or potassium where it's easy to just walk up and grab their electrons. They have a very low first ionization energy. My nonmetals' first ionization energy is high enough that in that tug of war for electrons, they will not give up and surrender the electrons. All right, so that leads us to the concept of polar and nonpolar. So a nonpolar covalent bond, and often the word covalent gets dropped and we just call it a nonpolar bond, are where the electrons are shared evenly. We'll specifically define that with electronegativity value less than 0.5. So something like a carbon-carbon bond is a perfectly nonpolar bond. It's perfectly even sharing. But even something like a carbon-hydrogen bond is still a nonpolar bond because we only have an electronegativity difference of about 0.4. So all of my diatomic molecules, as another example, are perfectly nonpolar covalent bonds. All right, so the other side of things are my polar covalent bonds. And once again, the word covalent is often dropped and we just call them polar bonds. And this is when electrons are not shared evenly. So we'll define this with differences in electronegativity values greater than or equal to 0.5. And I have a little asterisk here because we do get to a point, as we'll see soon, and we just talked about it in the last slide, where if the electronegativity difference is too large, it actually becomes ionic. So what about something like HF? Here we have a very large difference in electronegativity values, so this will be a very polar bond. And carbon to oxygen bond is polar, carbon to fluorine bond. What about that aluminum to iodide bond we talked about? Here it's a metal and a nonmetal. What kind of bond would that be? And there we said that that actually does form a molecule, so that'll be a very polar covalent bond. And what about something like sodium and bromine? They have a pretty large difference in electronegativities. And in this case, the difference is so large in electronegativities that it's not a polar bond anymore, that this is actually an ionic compound. So if we get the difference in electronegativities too large, it goes from being a polar bond to being an ionic compound. All right, so what is the result, the implications of having a polar bond? All right, so first off, we're going to result in partial negative and partial positive charges. which we indicate with the lowercase delta symbol here. So we have a delta minus and a delta positive to indicate that partial charges. So the more electronegative element pulls more on those shared electrons, becoming partially negative, and the more electropositive element becomes partially positive. So there's several different ways that these charges are shown. One would be as a cloud of electron density. We can show them with those symbols, the delta plus and the delta minus. And then we could also show it with an arrow that has a plus sign on it. So the plus sign is on the species that's a little bit more positive, and the arrow is pointing to the more electronegative element. Think about it as pointing to where the electrons spend most of their time with the more electronegative element. And these are images of that. So this first image here would be different electron densities. And if we have a bond between oxygen and hydrogen, then here's my shared pair of electrons. And you notice that the electron density is much more around the oxygen atom than it is around the hydrogen atom, because the shared pair of valence electrons spends so much more time over here with the oxygen. All right, so another way that we can show that is using arrows. So the plus side of that arrow is near the less polar, or the less electronegative or more electropositive hydrogen atom, pointing towards that oxygen atom. So once again, near the carbon, pointing towards the oxygen. So the arrows point to this species right here, where the electrons will spend most of their time. And then this is my last way that we commonly show electronegativity differences, to show those polar molecules with the delta minus and the delta plus signs. All right, so we have degrees of polarity, and this is from your textbook here. And this chart below offers general guidelines to help distinguish bond type. So it's important to note we're talking about most probable type of bond. It's not guaranteed, but it's just most probable. So we want to look at the electronegativity difference range. If we have a very small difference in electronegativity, like 0 to 0.4, then we have a nonpolar covalent bond. And an example of that would be a hydrogen to hydrogen bond with an electronegativity difference of 0. Next up, we can have a moderately covalent polar bond, and that would be about 0.5 to 1 difference in electronegativity. And an example of that would be a bond between hydrogen and chlorine, and the difference here is 0.9. So it's a moderately polar. And then if we get above 1 up to about 2, then we would say that's a very polar bond. So HF would be a very polar bond with a difference of 1.9. What about something like NABR? Also has a difference of 1.9. And we pointed out before that although this is a difference of 1.9, and our chart tells us, hey, that's probably a very polar bond, it actually turns out that this guy right here is ionic. And then we see another example of an ionic bond here between sodium and chlorine with a difference of 2.1 when we look at their electronegativity values. All right, so looking at polar molecules. Now here we want to make the distinction between a polar bond and a polar molecule. So polar bonds do not always make a molecule polar, despite what you might at first think. So in order for the entire molecule to be polar, we need a couple things happening. First, it must have polar bonds, clearly. And secondly, the charge in that must be distributed asymmetrically. So if you've taken a little physics and you recall your discussion of vectors, the way we would specifically say that is that the total dipole moment is the vector sum of the individual dipole moments. So if we have those different charges pointed symmetrically, as an example, if here's my central atom, and I have 3 polar bonds here, and they're all pointed symmetrically here at 120 degrees, then the vector sum of those is going to be 0. So this molecule right here would not be polar. So here I give an example, like let's draw the Lewis structure of water and carbon dioxide, and let's predict their geometries using VSEPR. So clear a little room here. and water's going to have 2 lone pairs of that central oxygen, and carbon dioxide is going to have 2 double bonds to that central carbon. Alright, so let's predict their geometries using VSEPR. Here I have a steric number of 4. I have 1, 2, 3, 4 groups around my central oxygen. 2 of them are lone pairs. So this is based off of a trigonal planar geometry. But those 2 lone pairs will make the geometry bent. And this structure right here, we have a steric number of 2 for my carbon dioxide. No lone pairs, which makes this perfectly linear. So because water is bent, and it actually can help to draw this structure being bent, that we see that this half of the molecule is going to be a little bit negative. And this half of the molecule is going to be, this half of the molecule is going to be a little bit positive, and this half of the molecule is going to be a little bit negative. Whereas over here, I can't have a half of my carbon dioxide that's a little more positive or a little more negative. That I have my partial charges of my slightly negative oxygens and my slightly positive carbon, but the vector sum of those pointed in towards the middle ends up being 0 here. So while carbon dioxide does have 2 polar bonds, because it's a perfectly symmetric molecule, it ends up being nonpolar molecule. So what would be other examples of geometries that can be perfectly symmetric? And these tend to be things that don't have lone pairs, although not always. The ones that I ask you to be really responsible for memorizing for your test are the ones that will have up to a steric number of 4. So steric number of 4 structures that will have a perfectly symmetric arrangement are things like a tetrahedron. And an example of that would be a structure like CF4, which has 4 very polar bonds, but the whole molecule is nonpolar because it's perfectly symmetric. Another structure would be something that's trigonal planar, where you have 3 bonds, so you could have 3 polar bonds and still be a nonpolar molecule. And lastly, my linear structure that we saw up here with the carbon dioxide. So one more time, a quick recap. What does it take to be a molecule itself that's polar? You have to have bonds that are polar, and that charge must be asymmetric. So if you're something like a tetrahedron, or if you are a trigonal planar, or if you're linear, even if you have all polar bonds, you can still be a nonpolar molecule. Alright, so let's test that a little bit more. Which molecules below are polar? And let's assume that all of these represented bonds are polar bonds. So looking through them, this guy in the top left is not symmetric, so this would be a polar molecule. P for polar. This guy, next one, is symmetric, so that would be a nonpolar molecule. My next one, also asymmetric, which would make this a polar molecule. Here I have a tetrahedron. Once again, nonpolar because it's symmetric. Nonpolar, it's symmetric. Polar, it's asymmetric. Polar, it's asymmetric. So we have to both look at the bonds and look at the geometry. Alright, so just for a little vocabulary word here, a word we'll often be using is dipole moment. And I just used it a moment ago, and sort of assuming that we knew what it meant, but let's just spell it out specifically. And the dipole moment is a measure of the polarity of a bond. And it's in units capital D, which are dBis. We're not really going to worry about defining that unit very much, but we'll just say that that is the unit D. To get a sense of scale of what that unit actually represents. tends to be on a range of about 0 to 11 or 12. So a perfectly zero dipole moment would be a hydrogen-hydrogen bond, completely even sharing, no dipole moment, so no partial charges anywhere. And then if we go way to the other extreme, something like potassium bromide, it's highly ionic, and it has a very large dipole moment of 10.5 D. So what do I expect you to remember for dipole moment? It's just the language that we're going to use to describe the magnitude of polarity, and I want you to be familiar with that language. All right, so now that we got a little bit of that background information out of the way, distinguishing between polar and nonpolar bonds, now we can get into our discussion of the intermolecular bonds, or often called intermolecular forces of attraction. And these fall into two large categories: hydrogen bonds and everything else. And that everything else we collectively call van der Waals forces. So with van der Waals forces, these are the sum of all of the forces between molecules other than those due to the covalent bonds or hydrogen bonds or ions. And there's three big types of van der Waals forces that we'll talk about: the Kilker forces, London forces, and the Dipole forces. So van der Waals forces together as a category are all three: the Kilker, the London, and the Dipole, all put together. And then hydrogen bonds are sort of their own special category, where they really tend to be my strongest intermolecular attraction. All right, so why do we care about intermolecular bonds? What's really the importance here? So my intermolecular attractions, they have a large influence on a number of macroscopic phenomenon. Things like vapor pressure, adhesion, conformation of biological macromolecules that you guys talked about in biology, cell assembly. They have huge implications for life, for the formation of molecules, for the physical properties of molecules. And as I said, they're also directly responsible for many physical properties, things like melting point and boiling point. And as we've said several times in the earlier videos, when we melt and boil molecules, we're not breaking covalent bonds, we're breaking my intermolecular bonds. So it should be noted that melting specifically will loosen those intermolecular attractions, but boiling completely breaks them. So therefore, boiling makes the best direct measure of the strength of an intermolecular bond. And often when I'll list values for intermolecular bonds to gauge their strength, I'll be listing out the boiling points because that's my best indicator of strength. All right, so let's start looking through those van der Waals forces that we talked about earlier. So my first van der Waals force is the Kilker force, also called Dipole Interactions, and that's actually the language your textbook uses. So these Kilker forces or dipole interactions only affect polar molecules. And my electrostatic attraction, because once again, every single force we talk about is an electrostatic force. All that changes is what are the positives and what are the negatives. And here, I'm dealing with a partial positive to a partial negative, a permanent dipole to another permanent dipole. So these would be two polar molecules that have permanent dipoles. All right, so the London dispersion force, also called just sometimes dispersion forces or even sometimes just called London forces, are forces that affect all molecules. They affect polar and nonpolar. So my electronic attraction here is an instantaneous dipole to instantaneous dipole. It might seem a little odd what this instantaneous dipole is all about right now, but we'll talk about it more later. We'll get to it in a slide or two. All right, and then my third van der Waals force is the Dipole force, also called the induced dipole force. And in isolation, this only affects polar molecules. But in a mixture, this affects both polar and nonpolar molecules and even atoms. So the way the Dipole force works is that a polar molecule induces a dipole in another molecule or atom. That induced molecule can be nonpolar, therefore giving it an induced dipole. Or it can be even polar, increasing the strength of its dipole. So my plus and minus here is a permanent dipole on my polar molecule to an induced dipole. So that induced dipole, it can be inducing a nonpolar molecule, or it can be inducing a polar molecule. And then my last class, the hydrogen bonds. And the hydrogen bonds are a special, strong hydrogen-specific interaction. And my attraction here is the partially positive hydrogen to a lone pair. All right, so that was really just a quick overview. My three van der Waals interactions, my Keesom, which is the permanent dipole to permanent dipole, my Debye, which is a permanent dipole to an induced dipole, and my London dispersion forces, which is an instantaneous. Let's look at them in a little bit more detail. First, we'll start with the easiest to understand example, and this would be the dipole interactions. Once again, these are also called my Keesom forces. And here, I have an attraction between partially positive and partially negative. Partially positive to partially negative. Partially negative, partially positive. So these would be permanent on a molecule. An example of something like this would be if I had HCl. So my chloride would be partially negative, attracted to another HCl. So the partially negative chlorine would be attracted to the partially positive hydrogen. It makes sense. It's a plus and minus interaction here. The little negative guy here will go to the little positive guy here. There's nothing that needs to be induced in this case. Here's another example here. I actually have drawn out the HCl to HCl, and you see that this right here is my dipole interaction. That's the attraction between this molecule and this molecule. It's the partial negative to partial positive. Here's another example between ICl, that we have the molecule of ICl, and that these forces here attracting the two together are my dipole interactions. Also set up arranged over here where I have molecule attracted to molecule. And just to give you a sense that we never really have one molecule at a time that we're dealing with. We're really dealing with a lot of molecules at once. And this image right here shows how it might interact through a lot of different molecules all together. And you notice that there are repulsive forces at work here as well. That if we get the positives line up near each other, then we get the repulsion. And if we get the opposite charges lined up near each other, then we get the attraction. All right, my next force, my dispersion forces, my London dispersion forces. And this is caused by the random movement or dispersion of electrons within the electron cloud. This is the only force holding together completely nonpolar molecules, but also acts on polar molecules. All right, so let's try to get a sense of what exactly is going on here with this dispersion force. If I picture an HCl and another HCl, it's very easy to see, well, why this might be attracted to this. They have the partial charges after all, so the little plus and the little minus will line up. But if we take something like an H2 and try to think, well, why would that be attracted at all, one molecule to another? What possible reason would these two have to interact with each other? And it would seem like they would have no reason. And clearly they don't have a very great reason, because the boiling point of hydrogen is just a little above 20 Kelvin. So there's not a lot of force holding these two together. But why is it not 0 Kelvin? Why is there anything at all holding them together? And here brings us into the concept of this instantaneous dipole. So if I picture my hydrogen atom here, I have my positive nucleus, and I've got my electron going around in its electron cloud. We're using the Bohr model here to try to illustrate this, and then say there's my 2 electrons. So these electrons are I probably should have drawn this up here. These two electrons are my shared pair of electrons right here. So every once in a while, just by random movement, that shared pair of electrons might end up being a little bit more over here. And when it's just a little bit more over there, just by random movement, because remember, what is an electron cloud? It's an area of probability of where you would find that electron. We never know 100% that it's exactly there, and this is just a cheap illustration, a way to try to draw where it's located. So if those electrons just happen to be a little bit over here on this side, then this side would have a very, very tiny partial negative. And let's say that there is another hydrogen H2 right over here. When this partial negative is near this other H2, then it is going to induce this electron cloud, and its electrons are going to want to get a little bit farther away. And it might cause this to have maybe a little bit of a partial negative charge over on this side, and a slight partial positive charge on this side. And maybe this molecule will influence another molecule. But we think about it as instantaneous because it's a fleeting effect. Every once in a while, bam, maybe there's a little negative over here. Or bam, maybe there's a little negative over on this side. That is just by random movement of electrons. Alright, so let's come back to my size here. Even though it's random movement, it's really important to note that it can be a surprisingly strong force. Yeah, we saw it was very weak in the case of H2, but it really can be very, very strong, and we'll look at some data for that. But this is arguably the most significant intermolecular force of attraction, despite what your textbook says. Dispersion forces, London forces, are really, really potentially very strong. So what are some things that can make this very strong? So it increases in strength with increased polarizability. If that electron cloud can be pushed around pretty easily, then it has a chance, greater chance, of having that partial charge move to one side or another of my molecule. So here I'm thinking size. Larger items have an increased polarizability. Another thing would be surface area. So think very large molecules. In surface area, people often tend to think, well, this is just my mass here. But it has a little bit more to do with the surface area being able to come in contact with the surface area of another molecule than it actually does with the mass. But things with large surface area are large molecules, so the points often end up getting muddled together. So we can see the halogens as a great example of this. We could see larger alkanes as a great example of this. So for example, let's think about my halogens. So increased polarizability is going to affect things. And we have some data looking at the halogens that tells us that this is the case. So if I think about the top, my FF bond, my CL-CL bond, maybe a bromine-bromine bond, and iodine-to-iodine bond, and sorry about that. So if I look at bromine at room temperature, this is actually a liquid, and iodine is a solid, where both of these are gases. So this bromine is polarizable enough that that dispersion force becomes strong enough to make it a liquid at room temperature. In an iodine, it's even larger and polarizable enough that it makes it a solid at room temperature. So the larger the atoms are, in a really small atom like fluorine here, is just a gas at room temperature, that it's not large enough to have a very strong dispersion force. All right, here's some other data just further emphasizing that point. If I look at something like benzene, this 6-carbon ring, its boiling point is 353 Kelvin. Naphthalene, which looks like 2 benzene rings together, and we increase my boiling point a little less than 140 Kelvin. So what I did here is I increased my surface area. So that larger surface area, you get a pretty decent increase in your boiling point. If I look at anthracene, 3 of them, I get another big jump in boiling point. Tetracene, 4 of them, I get another big jump in boiling point. I don't have an asterisk here because people aren't exactly sure what the boiling point of tetracene is, but this is just a predicted calculated boiling point. But look at this. These are perfectly nonpolar molecules. All we're dealing with here is carbon-hydrogen bonds. So why would I end up getting boiling points that are way, way, way high? 500, 600, 700 Kelvin. That should give you some sense that, hey, my dispersion force is not messing around here, that it is quite a bit stronger than you might at first suspect. And here's some other data that gives us an idea that, hey, maybe my dispersion forces are quite strong. I got the idea for this data from this site down here that I have credited at the bottom. But if you look at some fluorides, and we'll compare those fluorides to some alkanes. So here I have a 1 carbon fluoride, 2 carbon, 3, 4, 5, and 6 carbon fluorides. And this has about the same mass over on this side as a 2 carbon alkane, ethane, and then my 3, 4, 5, 6, and 7 carbon alkanes. So let's look at those boiling points in Kelvin. For my 1 carbon fluoride, about 195 Kelvin. If I compare that to my alkane over here, it's 184 Kelvin. What force is holding together this alkane? And this is only London. Only London. It's perfectly nonpolar. There's no other forces interacting there. So only London. And that London force accounts for this entire boiling point. So how much higher will that boiling point get by tossing on a hugely electronegative fluorine? A very, very, very polar bond and a pretty polar molecule. I only get a little increase here, about 10 Kelvin. You would suspect that when you are tossing in a very polar bond, and we're getting my Keesom forces involved here. See, here I have both London, and I have my Keesom, and I have my Dipole forces. All 3 of them are coming into play here, and that tells you that the Keesom and the Dipole are not having a very significant role. So my second fluoride, less than 5 degrees Kelvin, less than 5 Kelvin larger. And heck, even when I get down here, I'm about 6.5 Kelvin higher in boiling point only due to the London forces. So don't think that they're a very weak force. They're much more significant than you might at first suspect. Alright, so taking one other look at my Dipole force here. And the Dipole force is a polar molecule with a permanent dipole. Will polarize, distort, the electron cloud of a nearby nonpolar molecule. And what we get is an induced dipole. So let's take a look at how this might happen. Let's say I have an HCl here, and I have that HCl next to a nonpolar ClCl. The partial negative on my chloride will affect the electron cloud here of these chloride molecules. So the electrons that are around this chlorine are going to try to get away from that chlorine and move to the other side of the molecule, which will induce a dipole, a partial negative. What do you want to say?
I don't know.
You're not sure? Can you say hi? No, you can't say hi right now.
Don't say hi. I'm not.
Okay. Alright, that was just a little tiny Patrick interruption. Alright, to finish off on my Dipole force. So this polar molecule will induce the dipole on this nonpolar molecule. It will cause those electrons to move to the other side, therefore creating a partial negative charge on this half of the compound. Alright, that can also happen to another polar molecule. So a polar molecule can also polarize an already polar molecule. increasing the size of that dipole on an already polar molecule. The percentage effect of this force is fairly small, though, in a pure sample, but much more significant with something like a mixture. And here would be an example of the Debye force if I have nonpolar oxygen in a mixture with polar water. So here is my perfectly balanced nonpolar bond, but that perfectly balanced O2 comes near my polar water. And you see what happens here is that the electrons on this half of the oxygen, they try to move away from the negative electrons over here. As we know, like charges repel. So those electrons will move to the other half of the molecule, which makes this half partially negative and this half partially positive. And that's my Debye force, also called the induced dipole force. All right, so here's just a little bit of data about the percent contributions of these van der Waals forces. So I'll look at a couple different molecules here. So here's my molecules in polarity, and if I have something like carbon tetrachloride or benzene, things that are perfectly nonpolar, as I said before, the only force involved here is my London force. It's an instantaneous dipole. It's the only thing acting on perfectly nonpolar molecules. There's zero contributions from the Debye or the Keesom forces of attraction. But then let's see what happens as I start to go towards some polar molecules. So something like chlorobenzene, then look at this data, still 78% of that interaction between two chlorobenzenes, very strong polar bond there, is still dominated by my London force. Only 13% from that permanent dipole of the Keesom. Butanol, still, only about a quarter of that interaction between those two alcohols is dominated by the permanent dipole Keesom force. And then as I look at water here, water's a little different. Look at this. Water is 84% of my Keesom interactions. Why do we think water might be very dominated by these permanent dipole? And the answer here can't be the hydrogen bonds, because these are all van der Waals forces we're talking about. So why would water be so dominated by this? And it has everything to do with the weakness of my London forces. So what are things that made the London forces particularly strong? So we were looking for something that's very polarizable. Well, the oxygens and hydrogens here are not very polarizable. And we're looking for something with a very large surface area. Water does not have a very large surface area. So that's going to cause my London force to be pretty weak, and it's going to cause my Keesom force to be very strong. So the same is applying to ethanol, and even though ethanol is not very large, it is larger than water. And look what happens here. We might think that it would be dominated by my Keesom forces, but as I said before, this is a surprisingly strong force, my London force, that still it's the largest contributor to the van der Waals forces, even for something like ethanol, which is a 2-carbon alcohol. So not a very large molecule, not very polarizable, but still dominated by London forces. All right, and then finally on to the big guns, the hydrogen bonds. So what is it that makes hydrogen so special? I mean, it gets its own name for a bond and everything. Why hydrogen? The thing about hydrogen is that it only has one electron. So when that electron is being pulled by some really electronegative element, the atom is left very electron deficient, and it's essentially almost an exposed proton. Let's think about poor hydrogen. So here's hydrogen, and he's got one electron, and he's been searching to fill his octet, to get that second electron so it can have that noble gas configuration. And let's say hydrogen runs across somebody like fluorine. And hydrogen and fluorine, they meet on the street, and hydrogen's like, hey, fluorine, I really could use that electron. Really been looking for an extra electron. That electron's looking pretty nice. Maybe we could share. Well, what happens when hydrogen and fluorine get together? Fluorine's not messing around. It's the most electronegative element on the table. So it's going to, quote unquote, share with hydrogen. But man, that is about as uneven a sharing as you can get. Hydrogen's thinking, finally, my life's dream, my desires, my goals, they're met. I get my octet. But it's not much of an octet that it's able to achieve. That fluorine is pulling really, 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 really hard on hydrogen's electrons. Yeah, they're sharing, but it would be like if I sat down with my 4-year-old son to share a pizza. Let's face it, I'm getting more slices of pizza out of that deal. Fluorine is getting more electrons out of that deal than hydrogen is. So what's left home at hydrogen? So let's look at this a little bit more with fluorine and hydrogen. Here's my hydrogen atom. Let's try this instead. There's my hydrogen nucleus, that one proton. And here's my nucleus of the fluorine. And here's fluorine. And it's sharing that one electron with hydrogen. But that one electron that's being shared is really shared over here. It spends so much more of its time over here with the fluorine. So what's left behind? Almost an exposed proton. So what am I going to have happening here if you have an exposed proton? That exposed proton is going to be looking for more negative charge anywhere it can get that negative charge. So let's come back to my slide. What does that poor hydrogen do? Well, that exposed electron-deficient hydrogen atom, it's going to be strongly attracted to any other negative region. It's thinking, hey, I almost got my set of valence electrons, but it was a raw deal from fluorine. So it's going to go looking for any other negative charge to satisfy its desire to have its octet filled. Specifically, it will bond to a lone pair on another highly electronegative atom. And I say bond here because it's not really a bond, it's an attraction, it's an intermolecular bond. So what elements are electronegative enough to expose hydrogen's nucleus so that it goes searching for those electrons elsewhere? The big guns in the table. Things like nitrogen, oxygen, fluorine, my most electronegative elements. So when do I expect hydrogen bonds? Well, first of all, I need a molecule that's polar, and I need hydrogen that's bonded to my nitrogens, my oxygens, my fluorines. So what is the strength of the hydrogen bond? So we have to remember that with things that are hydrogen bonded, that we have hydrogen bonds, but we also have all of my other forces at play here. We have my Keesom forces, my Debye forces, my London forces. So things that are hydrogen bonded have hydrogen bonds plus all of those other forces. So the molecules in question are held together very tightly. And they are a combination of a strong dipole and a hydrogen lone pair interactions and are thus relatively strong. And here's a couple examples of some hydrogen bonds. Here would be between guanine and cytosine, and we see the hydrogen bond here between the oxygen and hydrogen. So specifically, we would say it's between the hydrogen's nucleus and a lone pair on that oxygen. That's the specific electrostatic charge. Here's another example between those, and here's another hydrogen bond. All right, here would be between a couple ammonia molecules. Once again, remember this is between this molecule and this molecule. And there you can actually see it's between the lone pair on that nitrogen and the hydrogen. Between the lone pair and the hydrogen. And this would be using water as well. Between the lone pair here, lone pair, and the hydrogen, that exposed nucleus. Lone pair to hydrogen. So it's important to note that inside these molecules, covalent bond, covalent bond, covalent, 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 covalent. But it's from one molecule to another molecule. Between the molecules, that's my hydrogen bond. That's my hydrogen bond. And then here's a larger example in DNA that we see, one of the great importance of intermolecular bonds. My hydrogen bonds holding together those two halves of my DNA. All right, distinguishing between intermolecular forces. All right, so here's the question. How do we know what forces are at play? So if we're holding together two nonpolar molecules, my only force there is London. It's the only one operating, and that's my instantaneous dipole. What if I'm holding together two polar molecules? Well, here are all my van der Waals forces. And we saw that London tends to be the most significant, but really all of them are at play here. If we're holding a polar to a nonpolar, is when my dBi force comes into play. But once again, London's always kicking around there in the background. London affects all molecules, but the dBi is the one force that's specific to having a polar molecule and nonpolar. And then what if I have hydrogen bonded to one of these big electronegative nitrogen, oxygen, or fluorines? And here's the hydrogen bond. But remember, all the van der Waals forces are at play as well. Let's look at how that affects my bond strength. And in general, from strongest to weakest, my ionic and covalent bonds here are much stronger. And the hydrogen bonds tend to be the strongest intermolecular attraction, and then all my van der Waals are lower in strength. And let's put some specific numbers to this. So if I look at an ionic lattice, here's my dissociation energy in kilocalories per mole. And we can go anywhere from 250 way up here to maybe 4,000 kilocalories per mole if I have a really tightly held ionic lattice. Now this is not necessarily the strength of one ionic bond, that it's holding together that entire lattice. So something like sodium chloride, that each one of those sodium ions is attracted to 6 different chloride ions. So the sum total of all of those represents the dissociation energy of my ionic lattice. But still, ionic bonds, very strong. Covalent bonds, we're talking about 30 all the way up to 260 kilocalories per mole. And then everything underneath are all my intermolecular attractions. And I say note that ionic and covalent bonds are always stronger than any intermolecular attraction. So hydrogen bonds are about 1 down to 12. To give a sense of scale in water, it's about 5 kilocalories per mole is just the contribution of the hydrogen bond. My dipole interactions, about 0.5 to 2, fairly small. In London dispersion forces, yeah, they can be really low. And I saw an example of when I have very weak London forces, like H2 attracted to another H2. And this would be extremely small, way down here. But boy, look at how high they can get. They can get way up there to 15. I mean, we see this. Look at iodine is a solid. All that's holding those iodines together are my intermolecular London dispersion forces. So while they can be extremely weak, they can also be extremely strong. And then one final thing we wanted to touch upon are network solids. And network solids are held together with covalent bonds, but we're not individual molecules here. The entire structure is all covalent bonds. You can think about, like, if you have a diamond ring, that diamond on your ring is like one big molecule of diamond almost. The entire thing is connected through covalent bonds. Same thing would apply to something like silicon carbide. So what kind of properties would we expect here? Well, we would expect these to be really, really hard. We would expect them to be really strong, and we would expect them to have very, very high melting and boiling points, which they do. Often they will even decompose or vaporize before they actually turn into a liquid. So network solids, it's sort of an odd case of my covalent bond, but it's the entire thing all held together with covalent bonds. All right, that ends our section on chemical bonds.